In set theory, we can write A minus B as A intersection of B complement. So to get the inclusion of A minus B, basically we are taking the things in A, but except anything that is in B. So if we take A and B as this, like Venn diagrams, and we need this A part, this part. This is the A part. We don't need this one, this thing. This part we don't need, no need. So what we're gonna do is we're gonna take B intersection, B complement, which means anything which is not B, which is the entire set except B, and we will intersect with A. Now we will get this part, A intersection B complement. Now let's move on to the next topic. To prove union is distributive over set difference. Union is distributive over set difference. This is a set difference. We can break it by this previous law we know, this one. Yeah. So A union B minus A union C. Now if you break it, here in the LHS part, it's very intuitive that A plus B C complement will be in the LHS. In the RHS, we can break it like this: A plus B, A plus C complement, and then from De Morgan's law, this thing becomes like A complement, C complement, and then here we see A complement A, C complement plus A complement B, C complement. Now this is due to idempotent law, this becomes 0, and this one becomes A complement B and C complement. So now you can see that LHS is not equal to RHS, so this statement is false, this is not true. Another statement we have that A intersection B minus C is equal to A intersection B minus A intersection C. Now we can break it. This one comes A, B, C complement, pretty intuitive. And now we break down this thing. We get this thing and then this thing, and when we get A, B, C complement, so LHS equal to RHS, this statement is true. Now let's come into derived operators. Derived operators are basically operators made up of primary operators. This is NAND, which is A dot B complement, NOR is A plus B complement, XOR is A B complement plus A complement B, and implication is A plus A complement plus B, and double implication is A B plus A complement B complement. The double implication we can either write in this thing, this double arrow, or we can write this XNOR. It is also called XNOR in Boolean. So we can write in this Boolean algebra as XNOR. Let's understand implication. So implication means that if P, then Q, which means that if P is true, then Q is true. The implication, you can see that if A is false, it means that either A has to be false or B has to be true. So here in the truth table, I have written the truth table for implication. You can see that here F is false. So either Q has to be true, either F has to be false or Q has to be true. So we can see that F is true, it is false, so we can say it's true. Similarly, if P is true, then Q. Similarly, if F is not true, then Q has to be true. So that's the reason we write true. Now here we see P is true, then Q has to be true. But since Q is false here, so we will write false here. Now if P is true, then Q has to be true. Like this. In these two examples, let me again go through it. Here F is false, but Q is also false. But in this logic, we are only covering if P is Q. Since P is not Q true, P is false, then we don't care about this true or false, so we write true. And here also F is false, P is false, so this statement is not valid, because if P is true, since it's not true, then doesn't matter Q is true or false. This statement will be always true. If you see this Venn diagram, like if P is true, then definitely it has to be under Q, right? And this is an intuitive approach. You can understand it. So if P is a set which is inside the Q, that means if P is true, then it has to be Q. Now let's see the properties. So one observation you can see that XOR gate gives us differences and XOR gives us similarity. In the truth table you can see that whenever one of the variable is complement and one of the variable is, like, let's write a truth table A, B, 0, 0, 0, 1, 1, 0, 1, 1. So in a XOR gate, this will be true. Like for XOR gate, these give differences because A and B are different values, so it will give us 1. Similarly, 1 and 0 are different values, it will give us 1, and this will give us 0. But if I write XOR gate, it will give me similarities. So if any values are similar, like this 0, 0 is similar, so it will give 1. 1 and 1 is similar, so it will give 1, and rest it will be 0. So that's the reason XOR gate gives us similarities and XOR gate gives us differences. So these are some properties which we can derive just from the fundamentals. Let's see, suppose this one. This we can write A complement of A complement and B plus B plus A complement plus B complement. Now you can see that A complement becomes A, and it becomes A, B, complement. So this is clearly XOR gate, XOR gate. So you can just prove it with the basic operators, and these properties will be coming to be true. Let's check for commutative property. So all operators are commutative except this implication and not sign, because it's intuitive that not sign cannot have any complement. These things we can prove with the basic operators. This why it's not true, let's see, because P implies Q means P complement plus Q. Similarly, Q implies P means Q complement plus P, which is not equal, hence it's not true. Rest other things are true that can be proven. Associative. So from simplifying this expression, we can say whether it's associative or not. We can have any expression and we can check. And one more key important point is that if variables in XOR are odd, then it will give us XOR gate. You can see A plus A XOR B XOR C gives us A XOR B XOR C. Similarly, if even number of variables, then it gives us the complement of the other gate, like A plus A XOR B is equals to A XOR B complements. This fact can also be proven. So let's give a brief summary. For commutative law, it's only not applicable for implies operator, implication operator, and for associative law, it's applicable for and or, but not for NAND, NOR, and implication. Let's come to distributive law. To check these are distributive, we need to check the expressions. Like if I want to say that A is distributive of B XOR C, then I need to check this. Like there are 2 operators, 1, 2, and there are 7 operators total, 1, 2, 3, 4, 5, 6, 7. So there are 7 C2 choices times 2 possibilities, that whether it's distributive or not. So we need to prove it. It's very simple. Now let's come into idempotent law. This law does not apply to derived operators, because P NAND gives us P dot P NAND. which is P. And so this is not idempotent dot is not valid. It's only for derived operators, which is A dot A gives us A plus A also gives us A. This is only valid for basic operators. Now let's go back, come to a question. Here you see I've given a truth table and the values of P box Q. Box is an operator which we don't know, so the truth table is given here. It's telling us what to do, like is it commutative, is it associative, or both and none. You can find out very easily. First we need to have the mean terms. We have this mean terms because this is 1, this is 1, so these are the two mean terms. So the expression comes out to be P Q plus P dot P complement Q. Now if you simplify, we get P complement Q complement plus Q, it gives us P complement. So this is the expression. So the box operator gives us P complement. If I write Q box P, it gives us Q complement. So this is not commutative. As you can see, this is not commutative. And then let's check whether it's associative or not. So we can write like this, and we simplifying, we get its P complement. Similarly again we write like this, and upon simplifying we get its Q. So these two are definitely not similar, so this is also not associative, so this is none.